Hello and welcome back. This will be episode 4 of solving some tasks of Rosetta code in Mathematica. So last time we solved a bunch and well, there's still a finite list left, either for tasks that have been fully defined or for tasks that are still in draft. So I selected just a few random ones and let's see what they are about. So I just selected these by title, but I didn't really read them yet in detail. So write a program or function to get the number of decimals in a given number. For num equals blah, decimal equals 3. For num equals blah, decimal equals 4. Note that the reference implementation in the ring language shows a function over a given number rather than a given numeric string, and that the sample values shown above are not enclosed in quotes. So what do people do? Python. So Python uses quotes. So it doesn't really use numbers, but it uses quotes. So I think, okay, let's make a new notebook just to try some things out. So I think if you have a number and I ask for the real digits, I think it will add a bunch of zeros, yeah? Yeah, okay. So the only real way that we can do this is also to use quotes like Python does. Decimal digits. So let's call this a real number that we input as a string. Well, actually we probably don't need them at all. So what we can do is we do string. Do we want to split it? So what if there is no dot? We have to think about that. Okay, maybe I do need the module. If string contains so if it contains a dot, then we are 0. Okay, so here we do string split r comma dot. We get the last one. I think we cannot simplify that. No. And okay, let's try this out first. Make sure we clear out the definitions. Let's see if we have some examples. Okay, everyone does kind of random things. So let's do an integer or multi-digit integer. The case that is just a dot, or perhaps something like this. Yeah. So the okay, yeah, this one we're already 0, it's a number. Here we just have to do string length. 3, 4, 0, 0. Oh, see here we have a little issue now with this case. So it says 2, because I think if I do, it will just do that. So can we give that little null string there? I don't think we can. So okay, rather than using string split, what we will do is we find the positions of the dots. So and since it is so let's say there is 2 dots, then what we want is to find the last one, since it's a single character. So let's call this position. And now we say string drop r comma pos. So let's call this, and then we want to do the string length of that one. Zero, zero, zero. Okay, that looks pretty sweet. Let's add it to this here. So the reason why I'm opening Perl is because the M of Mathematica is just before the P. No, not this one. Not this one. Here we go. We copy this. Yeah, and then the output. Well, it's just some integers, but here we go. Yeah, I don't need to see a preview. I think this will be fine. Looks all good. Do I want to save this? I think that's fine. All right. Write a method in your language which calculates the length of the major arc of a circle of given radius between two angles. In this diagram, the major arc is colored green. Sure. Please note, illustrate the use of your method. Okay. Major arc length. So we have a radius. We have, let's call it A1 and A2. And these are all numbers, presumably. And so I presume that these are indeed in degrees. So the difference between the two is this. What do I want to do? Yeah, let's do mod 360. So if people give very big numbers, then that should be fine. Let's call this delta. And then to get the major arc, I guess I have to create delta with 360 minus delta. So that will be our real delta. And then, so this will be an angular difference. Yeah. So we have delta. We turn it into degrees, which is, yeah, times the radius. So what is the example? A radius of 10, and then 10 and 120 degrees. Do we want to? Okay, what I can do is just do this. 43.6 something. Okay. Absolute. Maybe I should also do an absolute. Probably that absolute is a good idea. I think it will make a lot of difference for many cases. I don't see the equivalent of this to figure out to get the major arc. So let's see if this works. So that will always work, yeah. So the order doesn't matter. But I'm just thinking if you have, let's say 10 and 350, then here the difference will be 340. and 360 minus 340 will be 20 degrees difference, but that will be the minor arc. So in case of mine, let me just check. Yeah, so the major arc with 340 will be selected in this case instead of 20. So I think this code is actually wrong. Well, it will work for this particular example because I think you need something like this in there. Let's see, is there a max somewhere? Yeah, so here in Fortran we have this. But the rest forgot to include that. Bad people. Oh shit, I also closed that one accidentally. Here we go. So some of these are wrong, so we could leave a note like, oh guys, please fix this. Oh, the example was 10, 120, and well, let me just do this to show the numerical result. Ooh, delta does not show so nicely, of course. Maybe I just want to... Oh shit, I cannot press escape there. Let's just call it multi. Replace all. Yeah. So that covers a bit nicer, and the result will be this number. All right. Maybe I'll just put a little. This will select the major arc. Save page. All right. Here we go. Well, I could also add maybe this to my own code. So if I look at this later, then oh yeah, I will still understand it. All right, next problem. Next special primes. N is the smallest prime such that the difference of successive terms is strictly increasing and smaller than 10,050. Next special primes. Next special primes. Max. N is the smallest prime. So the difference of second terms is strictly increasing. Okay, so n goes from max of n plus 1 to the max. If so, it has to be a prime, and if it's a prime, the difference of successive terms. Okay, so I need already 2 here. Yes. Last difference was n minus 1 minus n minus 2. If I minus the last one is bigger than last diff, then we add it. Append to n comma I. Okay, this is now correct. 29, 40, 59, 10,049. That seems pretty good. That was surprisingly Easy. Copy this header. And we copy this. Remove the new lines. And of course, copy the output. Oh. Save this page. Boom. Piprimes? Piprimes? I'm not sure how you pronounce it, but I guess it's Piprimes. What was that? Piprimes. Pi of n, the number of primes smaller than n, where pi of n is smaller than 22. Okay, let's see what happens here. I think this is just the prime pi function, no? Zero, 1, 2, 2, 3, 3, 4, 4, 4, 4, 5, yeah. But the maximum should be pi. So I think we should do it like this, right? Minus 1. Here we go. 3 621s. 621s. Yeah. Okay, this was extremely easy in the Mathematica language. Here we go. Very short code. Answer. Do I want to really do it on one page? Maybe I can be. Let's call this pi, and I can do multi-column pi automatic comma 5 3. No, a bit more, maybe 10. What do they call direction or something? Appearance. Okay, let's make it 2 lines to make it a little bit easier to read. Because now I can copy this as a plain text, and this will be much better legible. Save page. Perfect. Do I want to save it? Well, I already saved it. It's a few kilobytes, but that's fine. Find the sequence of increasing primes q from 2 up to, but excluding 16,000, where the successor of q is the least prime p, such that p minus q is a perfect square. Okay. So the first one will be 2, 3. Okay, let's see. What is this thing called? Quadrat special primes. Big fan of the camel case. So let's say we call these our primes 2, and then what do I do here? From 1 to infinity if ps plus I squared is a prime. Ooh, do I want to iterate the primes or do I want to iterate the squares? Guess it doesn't matter for this case because it's only up to 16,000. Then, so if that is true, then oh, this should be the last of PS. Append to PS, comma. Let's save this. Let's call this Q. Q is that thing. Q. And then break this. So we break the. Okay, so 2, 3. Okay, and now we want to do that whole thing. We want to do it. Well, infinite amount of time. If last PS is bigger or equal to 16,000, then break. So I always find more than one then. So I guess I have to do PS most. So remove the last one. Yes, let's use this multi-column thing again. I don't know, 6 of them. Appearance horizontal. Maybe one more. Let's do. Yeah, this aligns very nicely. So here we go. We edit this page. Copy the header. Note that I use quite a bit of do loops. So most of the time you would not use do loops so much in Mathematica if you do data analysis. But if you want to find the first n of something where you don't know how many in advance, yeah, you end up writing do loops or while loops. Ah, shit, I have to do this. Robot testing. I am not a robot most of the time. Perfect. All right, this had an interesting title. So, non-transitive dice. Let our dice select numbers on their face with equal probability, i.e. fair dice. Dice may have more or less than 6 faces. The possibility of there being a 3D physical shape that has that many faces that allow them to be fair dice is ignored for this task. A die with 3 or 33 defined size is defined by the number of faces and the numbers on each face. Sure. Throwing dice will randomly select a face in each die with equal probability to show which die of dice thrown multiple times is more likely to win over the others. Calculate all possible combinations of different faces from each die. Count how many times each die wins a combination. Each combination is equally likely, so the die with more winning face combinations is statistically more likely to win against the other dice. If 2 dice X and Y are thrown against each other, then X likely to win, lose, or break even against Y can be shown as respectively. Example 1. If X is a 3-sided die with 1, 3, and 6 on its faces, and Y has 2, 3, 4 on its faces, then the equal possibility algorithm from throwing both and the winners is okay, 1, 2, so all the combinations, 2, 3, 4, 2, 3, 4, 2, 3, 4, 1, 1, 1, 3, 3, 6, 6, and then we have X wins, Y wins, or a tie. Both die will have the same statistical probability of winning, i.e. their comparison can be written as x equals y. Okay, so the total number of wins is 4, so x equals y. So these dice are, let's say, equal. In mathematics, transitivity are rules like if A operator B and B operator C, then A operator C. If, for example, the operator is the familiar less than, and it's applied to integers, we get the familiar if A smaller than B, B smaller than C, then A smaller than C. Alright, that's a very long read. These are non-transitive dice. These are an ordered list of dice where the bigger than operation between successive die pairs applies, but a comparison between the first and the last of the list yields the opposite result. Similarly, smaller than successive list comparisons with the final bigger than between the first and is also non-transitive. 3 dice, S, T, and U with appropriate phase values should satisfy S smaller than T, T smaller than U, and yet S bigger than U. The order of numbers on the faces of a die is not irrelevant. For example, 3-faced die described with the phase numbers 1, 2, 3 or 2, 1, 3 or any other permutation are equivalent. Sure. For the purpose of this task, show only the permutation in the lowest first sorted order, i.e. 1, 2, 3. A die can have more than one instance of the same number on its faces, 2, 3, 3, 4, okay. Any rotation of non-transitive dice from an answer is also an answer. You may optionally compute and show only one of each such rotation sets, ideally the first when sorted in a natural way. If this option is used, then prominently state in the output relations. Alright, here we finally go to the task. Find all the ordered lists of 3 non-transitive dice, S, T, and U, of the form S smaller than where the dice are selected from all 4-face dice, unique with respect to the nodes. Possible by having selections from the integers 1 to 4 on any dice face. Solutions can be found by generating all possible individual die and testing all possible permutations of 3 dice for non-transitivity. Alright, so I guess we first should write this function that okay, let's first save this. Rosetta. Let's call it die fight. Die 1, which is a list, and die 2, which is a list. Let's call it D2, maybe that's better. So we want to do all the combinations. So let me just try this example of 1, 3, 6 and 2, 3, 4. So then, yeah, and now, so what should this yield? We should subtract them from each other, and then check if they're positive, negative, or 0. Right? Yes. So I can use differences to do the differences between these two, but that will not be so fast, I would guess. But what we can do, let's call this sets. We can do So the difference here is 1, 2, 3, and here, so this should be y. So sine function, I guess is what we want. 1, 1, 1, minus 1, 0. Okay, and now I guess we just want to do total of that. 0. And I guess I want to do the sine of that again. Okay, so let's say this is an 8. Okay, and if this is, I don't know, 16. So if it's minus 1, the first die wins. If it's 1, the second dice win. And if it's 0, they're equal, let's say. So what kind of die? 4 faces with the numbers 1 through 4. So these are all possibilities, but let's sort them and delete any duplicates. So then I immediately fulfill this one, that lowest first order sorted, and so these are possible dice. How many are these? 35. So now I need to do subsets, range, length, ds, order 3. Ooh, these are a lot. Okay. So these are called subset indices. But then I still have to permute each of these. So what we do is we do permutations, if I recall correctly, yeah, on each of them. And then we catenate the results. And now, well, we have many more. And to be precise, we have almost 40,000 different sets of dice. And these integers are now indices that refer to these dice. So what we want is basically we want to run yes, so I guess what we will do is filter these. So let's first show how many we have. 30,000. So we want to select from this, and this should be -1, and this one will be hashtag ds hashtag, and then first part, a bit of a bracket mess. And there's the second bit. So that's roughly half the dice. And then the same between 2 and 3. Okay, but now, is it 1 and 3 or 3 and 1? Yeah, 1 and 3 should be positive. Ooh, only 3 sets. Yeah. One, 1, 4, 4. Ah, yes. We get 3 solutions because the first 2 can be swapped. So this is A. Let's see if I have the same one here now. Wait, did I do this correctly? Bigger than, so this should be 1. This should be the opposite. It should be like this. Okay. My bad. And now I think it is correct. 2, 4, 4, 1, 2, 3. Yeah, okay. So these are non-transitive dice. But now we want to show it in a nice fashion, I guess. So what we can do, number 1, number 2, and number 2, number 3, and not so convenient. So we turn this into a row. Maybe some extra spaces here. Maybe actually less spaces here. And then we want to turn this into a column. Here we go. Do we care about how long this takes? Not really, because it went pretty fast. Well, all this length stuff we of course don't need anymore. Here we go. That was a very nice one. Find the list of 4 non-transitive dice selected from the same possible dice from the non-stretch goal. So it looks for a loop of 4. Can we do that? Let's just see if we can do that. So if we turn this into 4, I think it is pretty easy. So this becomes 1, 2, 2, 3, 3, 4, and then 1, 4. Of course, there will be many more possibilities here now, and the exhaustive search I do now is definitely not the most efficient. Oh, and of course I have to change this now. 1, 2, 2, 3, 3, 4. And 1 becomes bigger than this. Well, I'm running it again. 1 1 2 2 2 4 4 2 2 2 4 2 2 3 2 2 3 1 2 3 3 1 1 4 1. Yeah, that's exactly what this guy has. So this is an F, or F sharp. In nim, let's see how people do it here. So we have this comparator function, and then it's quite a long. All right. Let's do above mini zinc. I've never heard of that programming language. So the code will be almost the same. So that is the code 1. And this will be the code of 2. Wait, so we don't need this bit. And actually we also don't need this bit. That one has been done. So I just need this bit. And then I hope this one copies nicely, but I'm afraid this AND does not copy so nicely. So what we can do is just do this. I also have to replace it here then. Perfect. Save it. Here we go. Let's do one more perhaps. Substitution cipher implementation. File encryption decryption. Encrypt on should be an N here, I think. Let's change it immediately. Encrypt an input source file by replacing every upper or lower case alphabets of the source file with another predetermined upper or lower case alphabet or symbols and save it into another output encrypted file. Then again convert that output into another file. This type of encryption decryption scheme is often called a substitution cipher. So, okay, we can do that. First we need the alphabet. So let's call this. Let's join that to from 0 to 9. So here we have, let's say, all the common characters. And now let's define a map of A towards random, is it random choice or random sample? I always confuse these two. I think it's random sample. Yeah. And well, for testing, we probably need to have. Let's thread this. Oh. Well, I think this is not so interesting, but let's put this in place. So with all the characters, maybe just to save some. All right, so we have a map from every letter to every other letter. Let's call this our map. Let's call it Rosetta. What's it called? Substitution cipher. Substitution cipher. So we need some example text. Is there something? I think this sounds about right. Do we have to put it to a file? Encrypt an input. Well, input. Let's make the function encode or substitute cipher encode. Substitution cipher encode. Input map. So what we do with it, I think we can actually do string replace. Input comma map. Is that really it? Let's call a string the quick brown fox. We have slightly different quotes. Here we go. Oh, we did not include exclamation mark and all those symbols. Well, I guess that's fine. Okay. Well, what we can do is to add a space. So then really it is different. So this is encoded. And now let's write the decode. And I just have to reverse all of them. I think that's it actually. Check. Yeah. All right, let's do that. This was pretty easy because we have this function string replace in Mathematica, which does all the heavy lifting for us. I think I had enough for today. Let's save this. Make sure that everything is correct. Maybe I should just add a little enter before this, so people know that definitions are here, and using the definition is here. Yeah, that's better. All right, let's go to the Mathematica page. Let's see how many are done now. So we have 1153 now, and well, there's still many more to implement. So here we have a list of still to implement, still hundreds to do. Well, we'll do a few at a time, and this also looks an interesting one, or this one also looks, well, many actually look very nice, and some I've already looked at, but either they took too long, or I didn't really get it, or because these are draft tasks, some of them. Sometimes the task is not really well defined yet, so I kind of ignored them because I don't want to waste my time on a not well defined task. Anyhow, this is it for today. See you all around.